Hello everyone, welcome to today's power electronics demo on inductor saturation. From the previous lecture, we learned that for a given magnetic material, the magnetic field strength H can be related to its flux density B through permeability mu. And when the flux density in the material is low, it is valid to assume that this permeability mu is constant and it is typically much higher than the vacuum permeability. However, once the flux density B goes beyond a certain limit, which we called the saturation flux density B set, the BH curve of this material begins to roll off, and the permeability of this material gradually drops to the vacuum permeability mu naught. This means that once an inductor is saturated, its inductance value would decrease. So in today's demo, we are going to see if we intentionally saturate the inductor in a buck converter, what the inductor current waveform will look like. Okay, so here is the buck converter demo board that we are going to test today. And here is the inductor component we're using in this buck converter. We can search online and find the data sheet for this family of inductors, and the specific part that we're using in this buck converter is highlighted over here. Its inductance value is 18 microhenries. In the data sheet, we can also find the typical inductance value versus current curves for this family of inductors. And here is the inductance curve for our inductor. At low currents, the inductance value is fairly constant. Here, as we can see, this part of the inductance curve is quite flat, and the inductance value is the nominal value, which is 18 microhenries. However, once we go beyond a certain limit in the inductor current, the inductance value will start to drop, and that is because the core material starts to saturate. In this data sheet, it provides us 3 different saturation currents that tells us when we will have 10% drop in the inductance value, 20% drop, or 30% drop. Here, as a rule of thumb, we will use the saturation current that gives us 20% drop in the inductance value as the saturation current for this inductor. So here we can say that roughly the saturation current is 1.5 amps. Now let's take a closer look at the experimental setup. So here is our experimental setup. We have our buck converter demo board over here. It is connected to a DC power supply and a DC electronic load. Right now, the input voltage is 12 volts. The load current is 1 amp. Okay. Here we are using an oscilloscope to measure the waveforms in this buck converter demo board. On the screen of the oscilloscope, I'm showing the input voltage in green, the output voltage in blue, the switch node voltage waveform in purple, and the inductor current waveform in yellow. Okay. So now, as you can see, when the load current is 1 amp, the peak inductor current is roughly 1.4 amps, which is below the saturation current of this inductor. And therefore, we can see that the inductor current waveform is in the ideal triangular waveform. We didn't notice any saturation happening over here. But now, let me increase the load current from 1 amp to 1.9 amps, and let's see what will happen. Okay, so now we have seen that the load current has been increased, and just to be safe, let me stop the waveform on the scope and turn off the E-load. And now let's take a closer look at the waveform shown on the oscilloscope. As we can see in this scope shot, when the load current is increased from 1 amp to 1.9 amps, the inductor current waveform is no longer in the ideal triangular shape. Instead, there is some distortion around the peak point of the inductor current. More specifically, the slope of the inductor current becomes larger and larger as the inductor current rises from its valley point to its peak point. We know that for an inductor, the slope of its current, di over dt, is equal to the voltage across the inductor divided by its inductance value. As the inductor current approaches its peak, the inductor saturates more and the inductance value drops. As a result, the inductor current slope becomes larger when the current gets closer and closer to the peak point. This is why we are seeing this spike on the inductor current waveform. Also, we can see that the peak-to-peak inductor current ripple has increased from 800 milliamps to 1.22 amps. Because of a larger inductor current ripple, the core loss in the inductor becomes higher and the RMS value of the current flowing through the switches also becomes higher. Therefore, as the inductor starts to saturate, we will see that the total loss in the converter grows faster than in the normal case, and the efficiency of the converter drops very quickly. Moreover, if the peak inductor current becomes too high, it may cause overcurrent in the switching devices and damage the converter. Therefore, in most cases, we should avoid inductor saturation when designing and operating a power electronics converter. All right, that's all for today's demo. Thank you and see you next time.